At the end of this video, you should be able to identify situations in which conservation of mechanical energy is valid, recognize the forms that conserved energy can take, and solve problems using conservation of mechanical energy. Chapter 5, Section 3, Conservation of Energy. Conserved quantities. When we say that something is conserved, we mean that it remains constant. If we have a certain amount of a conserved quantity at some instant of time, we will have the same amount of that quantity at a later time. This does not mean that the quantity cannot change form during that time, but if we consider all the forms that that quantity can take, we will find that we will always have the same amount. For example, the amount of money you have is not a conserved quantity because it is likely to change over time. For the moment, however, let us assume that you do not spend the money you have, so your money is conserved. This means that if you have $1 in your pocket, you will always have that same amount, although it may change form. One day, it may be in the form of a bill. The next day, you may have 100 pennies. And the next day, you may have an assortment of dimes and nickels. But when you total the change, you always have the equivalent of $1. It would be nice if money were like this, but of course it isn't, because your money is often acquired and spent, and it is not a conserved quantity. An example of a conserved quantity that you are already familiar with is mass. For instance, imagine that a light bulb is dropped on the floor and shatters into many pieces. No matter how the bulb shatters, the total mass of all the pieces together is the same as the mass of the intact light bulb, because mass is conserved. Mechanical energy. We have seen examples of objects that have either kinetic or potential energy. The description of the motion of many objects, however, often involves a combination of kinetic and potential energy, as well as different forms of potential energy. Situations involving a combination of these different forms of energy can often be analyzed simply. For example, consider the motion of the different parts of a pendulum clock. The pendulum swings back and forth. At the highest point of its swing, there is only gravitational potential energy associated with its position. At other points in its swing, the pendulum is in motion, so it has kinetic energy as well. Elastic potential energy is also present in many of the springs that are part of the inner workings of the clock. The motion of the pendulum in the clock is shown in figure 3.1 on the screen here. Analyzing situations involving kinetic, gravitational potential, and elastic potential energy is relatively simple. Unfortunately, analyzing situations involving other forms of energy, such as chemical potential energy, for example, is not as easy. We can ignore these other forms of energy if their influence is negligible, or if they are not relevant to the situation being analyzed. In most situations that we are concerned with, these forms of energy are not involved in the motion of objects. In ignoring these other forms of energy, we will find it useful to define a quantity called mechanical energy. The mechanical energy is the sum of kinetic energy and all forms of potential energy associated with an object or group of objects. All energy, such as nuclear, chemical, internal, and electrical, that are not mechanical energy is classified as non-mechanical energy. Do not be confused by the term mechanical energy. It is not a unique form of energy. It is merely a way of classifying energy, as is shown in figure 3.2 on the screen here. As you learn more about new forms of energy in this course, you will be able to add them to this chart.
The mechanical energy is the sum of the kinetic energy and all the forms of potential energy associated with an object or group of objects. In the absence of friction and any other external forces, the total mechanical energy remains the same. This principle is called the conservation of mechanical energy. Consider a pendulum of a clock swinging in the absence of all forms of friction. At each position of the pendulum, its mechanical energy is the sum of its potential and kinetic energies. At its highest point, all its mechanical energy is in the form of potential energy. As the pendulum swings, some of the potential energy is converted into kinetic energy. At its lowest point, all its potential energy has been converted into kinetic energy. As it reaches its highest point again, all its kinetic energy is converted into potential energy. It does not matter what position you choose, the sum of potential and kinetic energies is a constant value. The mechanical energy is conserved.
Mechanical energy is often conserved. Imagine a 75-gram egg located on a countertop 1.0 meters above the ground, as is shown in figure 3.3 on the screen here. The egg is knocked off the edge and falls to the ground. Because the acceleration of the egg is constant as it falls, you can use the kinematic formulas to determine the speed of the egg and the distance the egg has fallen at any subsequent time. The distance fallen can then be subtracted from the initial height to find the height of the egg above the ground at any subsequent time. For example, after 0.10 seconds, the egg has a speed of 0.98 meters per second and has fallen a distance of 0.05 meters, corresponding to a height above the ground of 0.95 meters. Once the egg's speed and its height above the ground are known as a function of time, you can use